record button so we do not forget. So let me go ahead and get started here. As I said, welcome. We're really happy to have everybody on board today. I did want to mention a few things that I usually try to have a tip of something new each time, would be a website, a paper, or something. So I'm going to go over two things very quickly. In my email, I mentioned Perplexity, and I'll pull that up. You know, GPT is the rage these days, but understand there are lots of ones like it, and pretty soon there'll be Bard from Google, and there'll be probably Bing from Microsoft. That'll be new search engines that'll do things differently. It's rumored that they will have citations or references, which to me is a step forward. My objection to ChatGPT is, well, where did they come up with that information? Well, Perplexity, Dave and I use several times every day. You ask a question, say about data science, and it gives it to you. It gives you a summary. It's hyperlinked. You can go straight there. So it gives you references. It gives you a variety of related information so you can search further, and you can ask follow-on questions. You can copy the link so you can share it with somebody, and you can put it on Twitter. But I'm just reminding people that this is different than ChatGPT in the sense that you actually see where they got the information, which I consider a step forward. Second thing, I'm making a recommendation. If you're new to writing papers and doing bibliographies and citations, PaperPal is a pretty decent choice. There's a free version with Google Docs, and I think this is a paid version. There are multiple ways to use it. In fact, if you're doing a single paper, it'll place your citations and create your bibliography automatically for you. And under cite, you just pick what kind of citation you want, APA, Vancouver. And then the way this works is I can search under here using the title, the author, the whatever URL. And then, so once the search comes up, you see it here, and then you hit cite, and that puts on the clipboard the citation. You can paste that into the bibliography. The only downside I've found out is it won't work with multiple chapters. It will do one bibliography, but it won't automatically do new ones for each chapter. But I'm just saying that's kind of one of my tips for the month, if you will. Chapter 2 has been a labor of love. It's certainly over 100 pages, over 100 citations, and over 100 images. It will be ready within the next few days. We'll send that out to everybody. I certainly think that's going to be important. So let's go ahead and get started. The way today is going to work, I'm going to not spend a huge amount of time on synthetic data because I want to leave enough time for Dave to talk about data science experimentation, which we think is key if you plan to be a data scientist. This is really like being any kind of scientist. You ought to have a systematic way to look at your subject matter, in this case, data. So I won't steal any thunder from Dave. I'll go ahead and get started with synthetic data. We got very excited with this topic when we found out there were 8 or 9 of these platforms available, many of them with free, at least trial versions and so forth. So we were very hot to try them out, but synthetic data has been out for a good number of years, but primitive initially. There was a variety of ways people did it. Ironically, they could generate it somehow with the decision trees and Bayesian networks. But to make a long story short, no question that AI, deep learning, is the way people are doing it nowadays, primarily with generative adversarial networks, GANs. I'm not going to at this time get into GANs, just understand that's what generates new images and new data is really what's primarily used. So Gardner, there's a quote there by Gardner that it's a fairly hot topic. Why would you want to do it? Simply to generate higher quality data and more quantity. The two major categories are you want to, again, generate more data, or you have a privacy issue where you want to share data, but you can't unless you de-identify it and it's approved, let's say, by your local IRB. Again, you need a lot of data for AI, particularly, less for machine learning. Obviously, HIPAA has stood in the way of sharing research, education, you name it. One thing that I've used is if you have a data set of, say, 200 patients that you think is really good, but you know that you ought to have more, you simply can generate what amounts to be a very similar data set. So now you've got 400 or 500 patients. I think that the potential there is huge because hospitals should be able to take some of their data, de-identify it, then synthesize it, and then share it with people, if nothing else, for education. However, it probably can be used for clinical trial, drug trials. And remember, when I put here reduce labeling cost, it actually costs about $5 per image or data set or whatever for somebody to label it. Let's say abnormal chest X-ray, normal. So anytime you can automatically produce labels, you've saved money. So again, it has potential for balancing a data set if you don't have enough of the minority class. It can, again, manufacture many more of those. Or what about feature imbalance? You don't have enough women in the study. You can manufacture very, I won't say identical, but very similar female patients to augment your data set. And it can be basically a sandbox for exploration. The first one I'm going to go over very quickly is Cynthia. I've written a fair amount on it. The two things to know about, it's a longitudinal data set. Looks like it came out of an electronic medical record. Patients, some of them are living, some are dead. That's very realistic. They have data that you can download. This is just an example. The bullets here, download as CSV file, but also as a FHIR format and CCDA. So it comes in more formats than just CSV. They recently published something on COVID, as a matter of fact. And the other thing you can do is you can also generate your own patients. There's a reference to GitHub where you download this patient generator and you put in what you want. I want 1,000 patients with diabetes. Now, my experience is if the incidence of diabetes in Massachusetts is 15%, it'll generate 15% diabetics, not 1,000 diabetics. But the point is it's highly realistic, but it's longitudinal. You'll have to tease it out. Some of the patients, for instance, have 10 years of lab work, but it'll generate for any query you have 16 CSV files. This is what you see. In other words, imaging, not the actual images, however, more of the fact that they've had it, the date they had it, what they had, and so forth. But realistic medications and vital signs and lab work and so forth. All right, let me move on to AI-generated synthetic data. This has been done, again, a bunch of different ways, as I mentioned, but really these days, it's almost all deep learning by either GANs or one of them we use something like recurrent neural networks. Along short-term memory is good at time series and sequential data. It actually outperformed the GAN for the studies that we did, which were not exhaustive, however. But we were a little bit surprised that LSTM worked that well. All right, when you judge synthetic data, there's three categories that seem to pop up in the literature. One is resemblance. How close is this data to what, the synthetic data to the real data? Utility, can you use it? And the example they always use is, can you create a model and is the prediction results for the model using real data and synthetic data pretty similar? Last, privacy is a little bit more complicated, but in essence, they don't want to have identical patients in the real data and the synthetic data. They're also careful about outliers because an outlier could be a patient that's unique and it stands out and could be regenerated. So there's a lot of ways you can show similarity. I'm not going to go over them. Dave actually came up with, I think, 35 metrics. But as you can imagine, and I'll show you, that basically showing that there's no statistical difference between the two. is the bottom line. You can do it with images. In fact, I'll show you an actual report from Gretel and show you what the report looks like of synthetic data. But this is an example of using Gretel. You might say, why did we select Gretel out of the 8 or 9? Well, they give you 15 credits per month, so enough to play with it. You can switch between the deep learning, so you have a choice of 2, and you can go in and customize it to whatever number of patients you want to generate. It also is actually a Python package. It also has an API. It has a lot going for it and good documentation. So what we did here, it is just showing you, this is the heart disease prediction data set, real data on the left, synthetic on the right. And you can look at minimum mode, medium, max, and so forth. But using a Wilcoxon rank sum test, which is like a t-test, notice the p-values, none of them are significant. Why? Because statistically, they're pretty darn close. So what else did we do? We looked at the parameters, like let's look at cholesterol, synthetic versus real, and the standard deviation, very close. And then we did a model. We tried to predict the presence of heart disease using the real data and turn around, use synthetic, very close. And then here, let me see if I can pull it up. You get a PDF or HTML file, but this is what Gretel generates for the report. It gives you a quality report, if you will, showing whether they had any problems, like resting blood pressure apparently was not quite as good. The rest was good. Here's a heat map that shows you the correlations for real and synthetic are pretty identical. This is a principal component analysis chart that's hard to see, but similar. And this is similar to what I already showed you. So it gives you both numerical comparisons and categorical data comparisons. So you can visually say, yeah, that's pretty close. Is it close enough for me to use for education, research, or clinical study? So I think, yeah, that's all I have. I strongly encourage you all, if there is a need to experiment, we're going to check with a local IRB close to where Dave is to see if they've already established any kind of criteria. I frankly, I have some concern that this is new enough that IRBs may not have established policies what to do with synthetic data of this high quality. So be aware they may ask a lot of questions if you attempt to do this. But it would be our recommendation, if you're going to use real data, to first take out the HIPAA identifiers and then go ahead and generate and discuss this with your IRB. With that, we'll leave time for questions at the end, but I'd like to go ahead and let Dave share his screen and he can talk to you about data science experiments. Dave, can you hit the share? Okay, okay, here we go.
You are sharing. Okay, all right, so. I assume everybody can see my screen. Good morning, everybody. So I'm going to be talking about data science experiments. So what in the world is a data science experiment? Let me first of all expand this a little bit here so you can see it a little bit easier. Well, a data science experiment, anytime during your predictive modeling adventures, whenever you have a choice, whenever you have an option, you automatically have an opportunity to set up an experiment. Now you might say, why do I get to do so many experiments? Let's say if you have a background in statistics, you say, I didn't have to do any experiments in statistics. What's so different now that I'm looking at predictive modeling, machine learning? What's going on here? Well, the problem is that we're always, when we're trying to predict the future, which is what we're doing with predictive modeling, and not just understand the past, things get a little bit tricky and things get quite complicated. And you have quite a few more options to deal with. Because, keep in mind, the future is the future, and it's not gonna easily give up any secrets that it has. So anytime we want to try to, tickle some insights out of the future, make a prediction about the future is not going to exactly cooperate and roll out a red carpet and say, okay, here it is. Here's your lottery numbers for next Friday, and all that kind of good stuff. And well, here's what the stock market's going to do in the next 3 days. Those kind of things are more fantasy than reality. So it takes a lot of hard work. And we're also fighting a very well-known, for the past three decades, there's been a well-known theorem called the no free lunch theorem. It's also abbreviated, NFL. Kind of interesting. We have an interesting NFL day tomorrow, so to say. And so it's a very interesting theorem. The no free lunch theorem tells us that, if you have a favorite algorithm and you want to use it everywhere because, you say, neural networks is fantastic and I read so much about it and there's a great hype with it and it sounds like a really cool name and I'm going to use it everywhere. Well, the no free lunch theory is going to come back and bite you. And what is the no free lunch theorem? What it means is that over time, not one specific algorithm is going to always do great with your data. And as a matter of fact, if you start out with one data set, and let's stick with the topic of neural network, and neural network just knocks it out of the park as far as the performance, the model performance metrics. It's doing a great job, and you say, "Wow, every time I go for something, I'm not even gonna look at the other algorithms. I'm gonna look at just neural network." You will be very disappointed if you follow that strategy. It's actually been shown for the last 3 decades in published articles and research that over time, all of these algorithms, if you look at, almost an infinite amount of different types of data sets to have them analyze, that on average, they're all do pretty much on average the same, which means one time's neural network's going to be fantastic, another time it's going to be terrible, another time random forest might be way up there, and who knows what's going to happen. So what we have to do in the world of machine learning, it's not like we say, like in statistics, linear regression, boom, end of story. Logistic regression, if it's a binary response, boom, end of story. No, not only do we have a lot of different algorithms we have to look at in the world of predictive modeling, but we have many different options inside those algorithms. And then we have all different types of modeling options. And none of these things are going to cooperate with you and just, the first one you try is going to be the best. So you always have to look at what are the options. Now, just to give you a feeling for what these options look like, let me show up the orange workflow that we sent out to everybody. And it's kind of an overwhelming type of workflow here, but this is one that you could set up for a master experiment. And here you got the workflow. We have the data is coming in over here. Then we're going to select which columns to do. We have some pre-processing. We're going to split the data. And then it goes into the test and score. We're going to see how good the algorithms are. And then you say, all right, where are the algorithms? Well, here I got it. Here I got logistic regression. I got naive Bayes. I have AdaBoost. I have random forest, logistic regression. I got neural network. I have KNN. I have gradient boosting. Those are all my different algorithms. And you might say, well, that doesn't sound like too many. Well, in reality, there are quite a few more. These are just, the top 8 that we looked at. And then if you look at, when I talked about different types of options, let me just double click here on logistic regression and see what's inside there. We see we have an option here. It's called a lasso. One's called ridge. And we also have this strength of the regularization type, no matter whether I'm using a lasso or ridge. I could take this bar and move it back and forth and make it strong regularization or weak regularization. And what is regularization going to do? It's going to have a look and try to make sure that I'm not overfitting the model. It's going to try to fight overfitting. It's also going to try to fight multicollinearity. So what I'm looking at right here, just on that one widget, I have two different main options of the regularization type. And I could have probably 4, 5, or 6 different versions of what's my regularization strength that I could experiment with. And I also have this other button that says, okay, you want to balance your class distribution. So just with that one button, I have a lot of different experimentation that I could do. And again, no free lunch theorem. There's no guarantee that if, Ridge or Lasso worked fantastic for me in the past, that's going to work fantastic for me today on this one data set that I have. And to make matters worse, let's say if I have a patient data set and I got a real live feed from a hospital and I'm trying to do predictions, and let's say I keep on getting new data to feed into that whole data set. What's going to happen over time is the new data you're getting in will kind of invalidate all your prior assumptions, and you'll have to retrain your models again and retrain your assumptions again. So you're going to want to set up new types of experiments. Now let's look under pre-processing. Under pre-processing, there's a whole bunch of different options that I have over here, but let's look at just one of them over here. Let's say data imputation. So what do I have in data imputation? I have, all right, it's saying, all right, if I have missing data, how do I want to impute for the missing data? Well, I could just tell it, average the most frequent data, or replace it with random data, or remove the rows on missing values. Well, right there, that's 3 different options. And you might say to yourself, okay, which one of these 3 are going to work the best for me? Well, unfortunately, the answer is it all depends on your data set. And you're going to have to then experiment what actually works the best. And it just goes on and on. There's different ways also to do what's called one-hot encoding or numerical values. And then we also have this very important step here of normalizing features. I could standardize it, I could center it, I could scale it, I can normalize it to a range of -1 to 1, or I can normalize it from an interval of 0 to 1. So I got 5 options right there. And to find out, and why do we even want to use normalization on features? We talked about that earlier, probably 2 sessions ago. Whenever you have data where the scales are incredibly different for different features, that can mess up some of the algorithms, but not all of them. And you might say, well, we'll just toss out the more sensitive algorithms and be done with it. Well, those sensitive algorithms, if you cater to them properly, they might be your best algorithm for that example. So you have to try to deal with and cater to the weakest link in your deck that you happen to be looking at. So you need to try to make all of the algorithms happy, all of the racehorses happy, so to say, because you never know which one of them is going to have a great day at the races and the great data with your data sets. And so you need to cater to them, and you need to make sure that experiment with them and make sure that they get what they need to give you the highest performance that they could possibly give you. So the list goes on and on and on. And we have in this chapter, there's just all kinds of information that we offer on this topic and give you all kinds of examples of what are standard experiments and other things. But you need to keep in mind that there's just a lot to think about. And again, when in doubt, experiment. That's kind of what you always need to think about. And whenever you have a choice, that's, fertile ground for an experiment. So let's move on through this chapter here. And it kind of highlighted some yellow areas here that I want to make sure that I've talked to. We have, throughout, this book so far, we've explained there's an 8-step process for data science. And whenever we talk about, and when anybody ever shows you, okay, these are 8 steps. Okay, do 1, then step 2, step 3, step 4. You say, okay, I could do that. I could follow instructions. I think I could do that. Well, here's the problem when you get into machine learning. Yeah, sure, we have some 8 steps, But there are a lot of things when you're doing predictive modeling where you actually go forward sometimes. You go backwards when things are not exactly, the model is coming out exactly what you expected. There are times you go in circles. So it is not necessarily a linear process all the time. Surely you start out linearly, but whenever you have choices, whenever you have surprises in your modeling and certain things happen, there's things that you need to do to react to that. And sometimes when you react to those situations, that means having to hop a little bit backwards. If you get a bad surprise, you might want to go back and say, maybe I should have experimented with something that I kind of ignored. And you're going to go back and experiment with something and see if the predictive modeling is a little bit better. So keep in mind, even though you see throughout the book, you'll see these 8 steps, and they clearly are 8 steps, but they are not totally linear. There's a lot of circular nature to the entire world of machine learning. And if you look very carefully in here, you could also see that we have an auto machine learning topic right here in the middle. It's a step. What we don't recommend is that, auto ML, okay, let's use that. Let's forget all this and let's just do auto ML. Well, auto ML is done actually pretty good in some Kaggle competitions, or Kaggle, however you want to pronounce it, and some other, international machine learning competitions. But the problem is they do really good, really fast, and then the competition might go on for several days. Is that it'll give a very good, respectable result, and then all of a sudden the humans will catch up to that performance level, and then they will typically beat it. Now, very often these auto MLs will get in the top 10 or maybe 20% of a lot of these competitions, but they are so far not the winners. And we got to also watch out that there's been a lot of hype about auto ML. Oh, I could actually clean your data. I could do this and that for you. But if you look very carefully and you look at the package you might be looking at, you'll find that there's probably more hype than actual reality involved in that. But one thing that we do say that it's not, if you're new to machine learning, or let's say you work in an organization where you don't have a bunch of data scientists. You can't afford even one data scientist. Let's say you're a small, mid-sized company or a hospital or a doctor's clinic. You can't afford, that type of expertise to put that person on your staff. Well, you could use an auto ML to say, okay, what result would that give you? And then what you do is you don't look at that as the final result. You then try to beat that result. You look at that and say, okay, how do I know when I'm doing my modeling, how do I know when good is good enough? Where's a benchmark so I know if I'm even in the right ballpark? That's if you want to use auto ML, we look at that as an opportunity to use it just as a benchmark that you're going to hopefully beat as you do your predictive modeling and you do your analysis. So I want to make sure I clarify that point. And then I talk a little bit more about the Kaggle competitions. Now here we have some, and I showed you a little bit, just a little bit in the orange workflow of where you have all kinds of options. And let me bring it back again, if it wants to come back, and it doesn't want to come back at the moment. So, but I'll show you a few more options a little bit later of what that looks like. And here we have it. So, any one of these workflows you get into, there are tons of different options. And let me, like, for example, data sampler. Just a situation, I make a choice here and say, all right, when I'm doing my modeling, one of the first choices I have to do is make a decision. How much of the data am I going to use for training? Here's set to default 70%. And how much do I want to hold back that the model cannot see, 30% in this example? So, and we're going to see if it can, how good of a job it does in forecasting that unseen data in the future. Well, guess what? I could take this little lever and move this back and forth all day, and do different types of percentages there. And I also have different options for the splitting. I could do a fixed sample size. I could use cross-validation. I could use bootstrapping. And there's other examples that I have. So again, wherever you have an option or a choice, you now have the burden of trying to figure out, okay, now, is my default setting really the best? I can click anywhere here. I go down gradient boosting. There's all kinds of default settings here. Now, are they the best? Well, they're a pretty good one, but it doesn't mean that if you experiment with them that you're not going to find a better setting. Just have a look over here. When I went under this one under gradient boosting, look over here. I have 5 different options right there. I have cat boost. I have skill to learn boosting. I have XG boost. I have that in 2 different versions, and so there's a lot going on there. And I have this lambda for regularization that I could play around with. I have different growth controls of, these are called hyperparameters that I could tune and play around with. So, and I have over here, the number of trees that I'm going to create and the learning rates. You might say, oh my gosh, I'm looking at, 4 in the top, 4 over here, 5. I mean, I have a lot of different options right here. I could lay out a huge experiment just in gradient boosting, just to try to make sure that I am giving that family of algorithms the best possible chance it can to make a great prediction for me. So guess what this is? It's all experiments. So you could just, spend your whole time saying, okay, I'm going to just kind of cross my fingers and use the default settings. Or, I have a very serious situation. I actually are doing some research here. I'm trying to save lives. I'm trying to make better predictions of how to treat patients better. In that kind of a situation, you might want to be a little bit more careful and a little bit more studious of how you set up your experiments. But you need to first understand and appreciate the opportunity of how many different, incredible amount of different options that are there. And every time, like I said, you have these choices, it's setting you up for an experiment. And then you see also this little widget right here that I'm moving around right now. It's called stacking. Well, guess what that is? Each of these algorithms right now, I'm going to get a score on. I'm going to see how well it did on its prediction. This is another option in the modeling that I could set up, which is stacking. What in the world is stacking? It's actually referred to as ensemble models. And what are ensemble models? It's actually a model of models. And you say, oh my gosh, what does that mean? Well, what it's going to do, and you can see there's a line feeding into that of each of these different algorithms, each of the 8 that I have here. And by the way, if all the different options I showed you, I could have 3 or 4 or 5 different just for logistic regression for each of these. I could have upwards of 20, 25, 30 different algorithms and algorithm options and widgets if I wanted to create a separate one for each of the options. And then every time I connect it also with this stacking widget, it's then looking how well would a model be if it took all the best features of all of the algorithms and try to minimize their cons. So it's trying to take the pros and minimize the cons of each of the algorithms. And it's going to give you a score by itself that it's going to call stacking. And it's going to show you how good this ensemble, this team of algorithms is done compared to the individual algorithms. Because keep in mind here, this is not like the Super Bowl. We're totally fans on one algorithm, one team. No, we have to be very, very open-minded in the world of machine learning. Again, keep in mind the no free lunch theorem, that there is no guarantee that your favorite team is going to win. So you got to be very open-minded, get everybody a chance, and then whatever the data set and the predictive modeling challenge is, give them all a chance, and then let the dice fall where they fall. And so this gives you just a little bit of a feeling here, again, going back for the different options. And here we have them listed, for example, determine the data splits. I talked about that. We have a lot of different pre-processing. We have the data imputation. I talked about that. Then we have the whole thing like Bob talked about earlier. we have, well, you might say to yourself, I only have 300 or 400 patients that I'm trying to do predictions on. But you know what? When I go on the Google developers website, they say, I should probably have at least 1,000 rows before I do any predictive modeling. So where in the world am I going to find, 700 more patients? I only have 300 right now. I'd have to wait another 2 years to get more patients. Well, that's where we get into the whole topic of synthesizing artificial patients. And we could then take that 300 database and we could beef it up to not 300, we could beef it up to 3,000 or 5,000 or 10,000 if we wanted to get it to a number where that we know that, if we offer the algorithm a lot more data to train, we might get a better response. And I say the word might, because there's always the big disclaimer in the world of machine learning. Again, we're trying to forecast the future, which is rather difficult. And so it is now ready for an experiment. If we're saying, okay, let's compare the 300 patients I have right now, and let me just do an experiment if synthetic data is going to actually give me a better prediction. Well, as Bob told you, that's not too easy also, as far as your choices and your options. Even within any individual company like Gretel that we've started to do some synthetic data experiments with, what you'll find is they have two different types of algorithms. And then you have, a variety of different types of synthetic data companies. So that's an experiment waiting to happen, where you might compare, Gretel against Y data against other types of synthetic data AI providers, because who knows, they might have a better mousetrap, a better version. So there's all kinds of experiments to be done there that could take up a lot of time. Then we have, there's just all kinds of things. Then if we have imbalanced data, it's also another type of way where that, let's say if I have a data set, let's say like on stroke, and only 5% of the people in that data set actually have a stroke, and then the other 95 don't. Well, I'm really trying to find out, how do I predict a stroke? I don't want to predict a non-stroke. They don't need my help for that. But we're trying to get smarter on, why do those people get a stroke, and how do I predict people in the future? But if I only have of a data set, only 5% of my data set are people with strokes or any kind of other disease or affliction or rare disease, you also have the opportunity to use SMOTE or Addison. And what is SMOTE? SMOTE is the same thing as synthetic data, but it's specifically used to beef up just that part of the data that you have that is underrepresented in that data set. And to make things even more complicated, if you Google SMOTE, you'll find out that there's, get this, 86 different flavors of SMOTE. And you say, oh my, are you kidding? No, I'm not kidding. There's 86 different flavors of SMOTE. And you say, well, why in the world would anybody in their right mind ever come up with so many different flavors? Well, you might have heard something like the no free lunch theorem, that maybe one version of SMOTE might not always be the best. And you might want to look at different types of ways of how, balancing a data set is maybe better using different versions of data balancing methods. Well, guess what? That's an experiment unto itself. You could read articles that have been published on SMOTE where they've actually gone through all 86 of these versions, and they will compare it on dozens of data sets, and they will tell you who the winner is. But the winner is on average, because for any one given data set, you could have any one of those 86 that could pop up as the winner. But the question is, what's going to happen if I test them on 50 or 100 different data sets? You could test that, but a lot of books, that when they try to give you and a lot of research articles, they're always trying to endeavor, okay, let's really find which version of these 86 SMOTEs is actually the best. In theory, if they tested an infinite amount of data, they'd probably all be pretty average the same. Again, because of the no free lunch theory. Depending on your data set, which is hard to predict in advance, a specific version of smote might do better than another version, just like all the other parameters we talked about. So it just goes on and on endlessly. What are the different choices and options that you have? And you could say, well, I read an article that said, that smote is actually, this version of smote is pretty good for balancing. Well, you could probably find another article that says it's not too good. So there's a lot of confusion and a lot of different methods. That you'll find articles where that this method is fantastic. You could find another article that says it's maybe not that fantastic. And the reason behind a lot of that variation you're going to find in publications, and it again all gets down to all of that stuff may be true for a very specific data set. But anytime you move from one data set to a new one, all bets are off. You have to start with your assumptions over again. And guess what that means? You have to experiment all over again. So the better you get at experimenting, the better you're going to be at data science. And if you don't like experimenting, then really your future and your success, let me put it that way, your success in the world of really coming up with the best predictive models in the world of data science is going to be quite limited if you're always saying, I only have the time to look at the default settings. Well, if you take the approach, well, I only have the time to look at the default settings, I don't have the time to do all the options, what you're going to do is you're going to limit yourself and your capability of finding algorithms and options and choices that are actually going to be better than what you had before. And then we have, item number 10 on the list here. All right, so we have, so what do we have here? We have principal components analysis. Okay, is that really better than ridge or lasso, which is also referred to as a a dimensionality reduction technique? Well, guess what? You'd have to experiment and see how that works out. So there's just experiments after experiments after experiments. And then when you're doing an experiment, we list here, there's 9 general steps, that you could do when you're trying to set up, effective experiments as far as, what's the legwork you're going to go through. So you got to go through all these steps. You got to come up with what are your research questions, what's the experimental design and scope and the data you have, and what's the data, is it clean, is it not clean, and you got to make sure that you're writing a data science experiment report and write your conclusions. So there's a lot of things you need to think about, and those are general steps during the experiment that are good to follow. Then what we also list here is that there's 5 different levels of complexity in these experiments. And the lower, less complex ones, let's call them a level 1, and you're dealing with a single factor experiment with very limited amount of choices. And then, as you can imagine, the higher I go up on my complexity level, I'm trying to compare multiple things at the same time, score them, find out what the performance measures are. And so the more you try to combine more complexity of the options in your experiment, it obviously adds to the complexity of the experiment. And I'll go here a little bit in detail right after this and explain certain things. But before I get into that, we need to understand that, each of these algorithm families, like logistic regression, random forest, KNN, that are listed on the left side of this chart here, they also have some random default settings inside of themselves. Again, I said the evil word defaults. There are times the word default's going to be your friend if you want to find a baseline performance that you're either happy with or not happy with in the world of predictions. But if you're not happy, you need to understand where the defaults are and what they are for each of the algorithm families. And guess what? You're going to want to turn off those defaults, which we can do in orange. And then you're going to want to experiment on each one of them one at a time to see if you could come up with a combination of pre-processing options that are actually better than the defaults. So there's a whole bunch of options waiting for you to happen right there. And you might say, oh my gosh, well, I could spend months on that. Well, In reality, what you might want to do, let's say if you did an experiment and you find out for, the top 8 different types of algorithms you're looking at, that you find that one family is kind of pushing on the top. Well, you might want to say to yourself, let me just stick within that family and do all kinds of experiments and see exactly how much more predictive modeling I could squeeze out of it. So those are considerations we got to look at. We also need to understand there are certain types of these algorithms and features inside of Orange that work well with other types of widgets and do not. So you need to understand that whole dynamics. And then we need to look at, you've seen enough if I showed you some of the workflows here already that we use and what are the options there. Now we got to look at, okay, what are the scorecards that look like? Now, when you go into the test and score widget, it's going to automatically say, hey, if you tested these 8 algorithms, it's going to give you its own little scorecard. And you could click on the top of these and it'll sort it by high to low, low to high for each one of these different types of experimental metrics. So you can see what's the good and what's the bad. So that's a simple experiment. When it gets more complicated, you might need to also take that information that you have from the test and score widget and start to enter that in an Excel spreadsheet document where that collects all of your information. And then you could rank that based on whatever metrics you're using and on whatever types of algorithms you're using. You could color code that with conditional format, and you could rank that high and low and see what's doing well for you. So like I said, you have this basic, I'll call it a level 1 experiment. And then when you get into the more complex experiments, you're making it wider, which means that you're making the list of performance metrics, you're adding to it. And if you're adding then to the bottom of the list, you're adding more algorithm options. And as you move down that list of complexity here, all of a sudden you say, oh boy, now that's a much more complicated looking workflow. Well, guess what? It's got a lot more different algorithm options that are listed individually. And they're listed there individually, so I can automatically, when I go into the test and score widget, it's going to show me their scores automatically that I can rank. So that's a more complicated experiment. This is an example of a very expanded test and score widget that shows you that complexity and allows you to then sort that. And then, as you move on higher with that complexity list, again, you might want to go offline and take the information and add it to an Excel sheet that you could use as your main scorecard. And we've sent, a template of this out to each of you before this session today. So, and then the experiments can get more and more complicated. I can have experiments where I'm adding metrics upon metrics and more metrics to make the experiment wider. And then there's other experiments where I'm adding more algorithm options to the bottom. So just, just kind of graphically showing you. And then in the highest level of complexity, not only am I adding for each of these scorecards, more to making it wider and deeper to add more options, I'm also adding totally different alternate options that I want to comparing it with. For example, here, I got no data imputation. I got imputation method A, B, and C, and I want to compare all of them. Well, I need to do all this analysis for each one of those. So that gets into very complicated styles of algorithms and experiments. And then, as I already showed you, when I click on each one of these basic algorithm families, and I've circled that here in red and green, all the different possibilities that you have of entering different numbers and doing what's called hyperparameter tuning, of which is that in itself is a wild experiment just for any one of these algorithms individually. So you can see the world of experimentation never ends, and it seems rather complicated, and it is. And we try to do our best to show you how to plan for these experiments and how to set them up. And then, the tedious part is then doing the experiment and then interpreting all of your information to that point. So I think what I'll do right now is I'll stop talking and leave it open for any questions. I can see there's a lot going in the chat there. I assume that Bob, you've been answering some of those, but Let me just open it up for questions now. Then we're also trying to entertain some of the chat questions that might have been asked, but maybe have not been answered yet.
Yeah, and Dave, I have answered most of it. I think Iman
Wonderful.
has a concern about synthetic data in terms of it could worsen bias. We know that there are potential risk of all models for bias to begin with. I don't know that I have any words of wisdom about that. I said that this would be another area where you'd want to experiment, looking at what changes happen with adding synthetic data. Do you have any other comments about that subject?
Nope, just back to the first thing I said is, when in doubt, experiment, which is exactly in line with what you're saying, Bob. And you could try to find, infinite words of wisdom in various books, but you're going to always find disclaimers in the best books and articles that it all depends on your data set. You'll find that disclaimer all the time, that people will be, that they will, they'll try to hold themselves back from giving you so-called global truths.
Yeah, I mean, so you're going to hear us say it depends all the time, basically. And it's not hedging, it's simply saying the results vary based on the algorithms, the data sets, the defaults, the hyperparameters, and so forth. I did want to point out that this is trying to set the bar considerably higher. Some of you all may be happy with just exploring data with some basic descriptive statistics, basic visualization, maybe creating a simple model, and that's perfectly okay. But if you want to get to the point where you're doing more competitive, meaningful data analysis, then I think you need to understand the data challenges that we've gone over, as well as setting up experiments. So if somebody asks you, did logistic regression actually work best, you're going to be able to say to them, yes, and give a great deal of details. And they're going to say, did you use regularization? Did you use L1 or L2? You're going to be able to say what exactly you did. So this raises the bar up to the level of how the data scientist should think and is trained to think. So that's why we're going over this detail. And I've not seen, to be perfectly honest, I've not seen this in any textbook or any web article that I have seen. David has done an incredible job of making this easy to understand and emphasizing its importance.
Yeah, what's interesting, if you Google data science experiments, you will get all kinds of hits of people and services and companies that will tell you, we can help you track your experiments, but they won't tell you how to set up an experiment. Because they know that, if you do an experiment, you might get yourself lost in your own data. So they will, there are services and software just to kind of like program management software that help you guide of, what did I do first, second, and third to walk you through that. But yeah, you're not going to find these types of depth that we could find anywhere when we Google this topic. Any other questions?
Yeah, there is
Comments?
a question by Shingarai about sample size, which we haven't really discussed. And it's kind of separate, but it's a legitimate question about, do you worry about sample size in an experiment like this?
Yes, sample size is always a big question, and there's a way to get around that. Let's say, for example, that you have, let's say if you go to, again, the Google developers website and they say, rule of thumb, and again, you got to always watch out with rule of thumbs. You need 1,000 different rows. Well, guess what? You could immediately invalidate that by, there's other rules of thumbs that say, well, you should never have X times more columns than you do rows of data. And then you might say, okay, now what does that mean on, okay, so how do I deal with that? Let's see if I have my magic 1,000 number of patients, but I also have, 1,000 columns of information that I want to correlate it to. How do I deal with that? Because then all of a sudden you might not have enough data because of the ratio between your columns or predictors and the number of data yourself. So how you get around that is through what's called dimensionality reduction. We get around that by principal components analysis with the lasso regression. So again, how do you know if you have enough data for an experiment is if you start to violate some of the basic rules of thumbs and more columns, then you need to experiment with, the word experiment again, different methods of dimensionality reduction, which means you're going to then knock out a lot of those columns because your analysis is going to prove that they're either correlated highly with each other or they're really not a high correlator at all with the end game. So it's safe to knock them out. So again, the answer to that question is it depends. And again, if you think you have enough, but you're not sure, you could run the experiment with the data you have. And then you could also run it with, like Bob was talking about earlier, synthetic data, and say, I want to have 10 times more data and see if that changes the results. So again, that's another experiment.
And, there are online sample size calculators. I think that's really done for routine statistical studies. I'm not sure if that's for machine learning models. I will look into that and personally get back to you about it. I mean, classically, you look at what do you consider to be a statistically significant or clinically significant effect of your intervention, whatever it happens to be, a new drug or whatever. And you can base it on that. You can base it on confidence intervals. You can base it on effect size, which we haven't gone over yet, because we're getting away from p-values. I mean, as you all probably know, that's very limiting. But I will try to see if I can find an article a little bit better on sample size specifically related to machine learning models. Other questions, though, about either the DSC or more about synthetic data? We do hope this is takeaway information. We hope you will play around with Gretel or which one you choose. I think it's worth doing, and I think you'd be impressed. Second of all, we would hope that you would learn to have a systematic way of approaching a data project, a data experiment. They're all experiments from the way we look at it. And you get better and better at it. There's no question practice makes perfect, and there are no real shortcuts. Any other questions? We will, again, tape this, and I'll send out a notice later today. So for those people who weren't able to attend, they can look at it after the fact. I see a raised hand. Sedalia?
Hi, hello everyone, and thank you so much for arranging this virtual sessions. It's been a pleasure to be with all of you. For me, I think I had a read before the session, and I was looking at the process of actually doing a project. And I finally started doing some data science with Python, finally. And what I found really hard is using like data sets. So we have to use data sets that we don't know anything about. And is actually looking at what's the question, how is the data organized, and then how do I kind of take that and then develop the whole process, and then how do I control for missing data, how do I control for errors, precision. I find it really hard. And is the whole testing and all defining the testing sample size and all those things. I find it really hard, but it's been quite interesting. So yeah.
Well, and I think, though, what you're saying is what data scientists will admit to you, and that is this can be hard work, that 75 to 80% of their time is spent doing this, not pushing the run button, to run the model. That's the easy part. So this is where the rubber meets the road, and it is laborious. And I don't think it's boring. But the point is, there is a process that you must go through, a logical process. Otherwise, you're being really superficial, and you have to admit that. But this gives you the method to do an in-depth data science experiment that you could be very proud of. Other questions or comments? Feel free to unmute and ask away.
Yeah, the question is with this is that who do you discuss it with? Because this is quite complex and majority of people, especially those that are starting, don't know exactly exactly what they're doing. So the question is, is there a group where a bunch of people that are trying to learn these much more complex methodologies can come together and actually discuss, their experiments and actually try to understand exactly what have they done? Because majority of the times, I'm still very basic, but I need to figure out how to understand all that data. And sometimes I don't think that's so easy as we picture it. Mm.
There's a lot of different discussion boards where data scientists get together and they'll just throw out, even people will tell you, I'm a newbie, I'm a beginner, and I'm trying to do this. And am I on the right track? Something as simple as that. And there are discussion boards where there are people that have more experience. You hope that they have, that they will actually, communicate with you. But you just got to watch out that you don't know maybe much about these people, and you need to just understand that that is just a random voice in the wilderness, and it might enlighten you, but it also might confuse you. But I think discussion boards should not be ignored, and they're also an interesting source for different opinions. If you're like you say, who do I talk to? Well, that's an option to talk with a group.
Yeah, I think that's really important. We do like to promote the idea of mentorship. David and I will certainly try to mentor people the best that we can. It was particularly important for programming. I've done my share of Python, but without a mentor. And I can tell you it would be much better if I had a data scientist or somebody or computer scientist that I related to easily and clearly, that I could ask questions every time I ran into a problem. Office hours, for those of you all who may or may not know it, this was started related to the artificial intelligence in medicine board review course, but every Wednesday at 12 o'clock Eastern time, Dr. Anthony Chang has office hours for an hour where you bring up anything. And it's a good place because the people logging on are data scientists and a variety of people. You may be able to get a name or at least get somebody's attention for help, particularly if it's AI related. If anybody wants to know more about office hours, they can just email me because it's free and open for people. Any other questions or comments about the two topics we covered today? Next time, by the way, we'll be pretty well going over all the orange widgets, how to use them. Whether we can do that in a whole hour, I don't know. But basically, we'll be going over some really important orange widgets, and we'll probably touch on JASP, JASP a little bit then as well. Other comments or concerns? If not, we'll look forward to having you all next month. And we appreciate your questions and your participation.
Thanks, everybody.
Thank you.
Okay. Have a good Super Bowl weekend.
Yep. Bye
Okay.
now.
Bye-bye.